So next speaker is Jim Palmer. He is Royal Society Research Professor at Oxford. That's Oxford in the UK, not in Ohio. And he's also spent time at the European Center and the Met Office, a lot of time at the European Center, as I remember. And he's a member of the Kohler Advisory Committee, as well as a skilled musician, plays the guitar and composes on the fly and so forth. So, and he's going to talk about unifying weather prediction, gravitation, and quantum mechanics. Is that right?
Looks like I turned up at the wrong Oxford. I've actually slightly changed the title, well, not so much the title, but this byline. I guess we don't need two microphones, do we? Because I was thinking back, you know, I've had collaborations with Shukla since the early 80s. I think we first met in Liège for the, was it first, I don't know, coupled ocean atmosphere modeling conference. But the collaboration that I think, on the one hand, was the most exciting, certainly on the other hand, the most frustrating, but probably on the third hand, the most important, was the climate modeling summit that Julia alluded to, and the idea for which was actually, I think, hatched in the JSC in Zanzibar a couple of years before. So I want to give a talk which I'm going to return to this aims of the summit at the end and try to provide some sort of my own sort of perspective on how I've slightly changed my views about this, only very slightly. I'm going to be seamless, so I'm going to start with weather and move through to climate. And I want to start with a quote from the late Alan Murphy, who was one of the pioneers of probabilistic verification. And I hope people will resonate, because this certainly resonates with me. Forecasts possess no intrinsic value. They acquire value through their ability to influence the decisions made by users of the forecasts. And I think both Lou and Julia, sort of in their talks about how the weather services are evolving, made great play about the value of weather forecasts to influence decisions. So at ECMWF, for a number of years now, one of the metrics that we use to evaluate the value of the forecasts is this simple decision theoretic model, which in fact Alan Murphy made popular. I think it actually goes back to Anders Angstrom, who was the grandson of the famous Angstrom of atomic distance fame. And what it does is attempt to show the potential economic value of using a forecast to mitigate against some potential hazardous, let's say, hazardous weather event. And the idea is along the x-axis, you imagine a spectrum of users who are represented by their so-called cost-loss ratio. And they make decisions about whether to take protective action against a weather event. And the key point is that if you have available to you a probability forecast, your strategy is actually much more informed and much more valuable than if you just had a deterministic forecast with no flow-dependent estimate of uncertainty. So if you have if you have a small cost-loss ratio, then you would take protective action even if the probability of the event was small, whereas if your costs of mitigation relative to the potential loss were more comparable, you would only take protective action when the probability of the event was close to 1. The point is that what this shows very clearly, in ways which other metrics don't necessarily show quite so clearly, is how much of a benefit an ensemble system has over a deterministic system. So these are actual metrics from the ECMWF forecast system. This blue being the ensemble, and this being the high resolution. So higher resolution model, but has less value, and in fact for some range of users has no value at all over climatology. One of the other contributions that Alan Murphy did was to essentially show that a skill score called the rank probability skill score, here I've used the word continuous, or the letter C, continuous rank probability skill score, which is a common, I mean, Ben Kirkman spoke about it earlier, is a common probabilistic skill score. I think for people who don't know continuous rank probability skill score, it sounds terribly kind of arcane and something that only an expert in probability forecasting could ever understand. But the key point that Alan Murphy made was that this CPRSS is essentially the value of the forecast integrated over all users, i.e. overall cost-loss ratios, and all events in the probability distribution of the weather event. So CRPSS is intrinsically tied to economic value in ways in which anomaly correlation or RMS error are not. So in my view, if we are serious, as Lou and Julia said, we have to move to this type of score as our primary metric for evaluating NWP skill. And I think we have to move away from anomaly correlation and RMS error in the future. So when we compare scores, don't use these 500 millibar height anomaly correlations. Use CRPSS for precipitation or surface temperature or wind speed or whatever like that. So Ben Kirkman gets my gold medal for using this metric. Lou, I'm afraid you've only got a bronze medal this time, but for Shukla's 80th, I'm sure you'll be up there. Now, one of the reasons for saying that is of this first point of my talk is to say that another kind of passionate interest of mine, which is developing the idea that our subgrid parameterizations should be inherently stochastic in nature. I don't want to go into the scientific reasons for this, but essentially it's due to the fact that if you look at the spectrum of variability in the atmosphere, it satisfies a scaling law with wavelength, and because of that, there is no scale separation between resolved and unresolved processes, so the conventional deterministic formula doesn't really have a good scientific basis. So for years, we've been promoting this idea of stochastic parameterization, and what I want to show you here is that it has quite a profound impact on this CPRSS, particularly in the tropics. So this gray line is basically forecasts without any representation of model error, and these are various flavors of stochastic parameterization. In the extratropics, the impact is more subtle, but it's still positive. I wanted to make the point that the stochastic parameterization has an important role in climate simulation as well. Actually, at the last minute, I took out a slide, which slightly in retrospect now I regret, which shows the sorts of weather regime analysis that Christiana Stan showed with superparameterization. And we get a very similar positive impact of stochastic parameterization on these weather regimes as the superparameterization does. And it does raise the question whether there's some linkage there between the mechanisms by which superparameterization and stochastic parameterization works. But I wanted to instead just focus on this result, which I'm afraid has come out a bit washed out. These are some results by a postdoc in my group, Hannah Christensen, who's been working with Judith Berner at NCAR. And it's looking at a multi-century integration of the NCAR CAM4 coupled to an ocean, a 1 degree ocean. And this shows the ENSO, again, a power spectrum in time of ENSO variability. Now, unfortunately, I can't even see it there. The observations are, well, let me just take my word for it. The observations come around something like this. Basically, this is the standard deterministic model, which has a much too sharp peak at sort of 3 or 4 year timescale, whereas the observations has a much redder spectrum. This is with stochastic parameterization. Now, again, what you can't see here is that the scale, this goes up to, 100 or something. This only goes up to 50. So the observations are now actually much closer across the range of, so here we're looking at decadal scales. It's kind of reddened the spectrum and flattened out the spectrum. Now, this is with just stochastic parameterization in the atmosphere with a decorrelation time of 6 hours. So the stochastic scheme doesn't know anything about these multi-year timescales, but presumably from some nonlinear processes, it's affected the power spectrum on these timescales. We've looked at a number of simpler models. We've looked at the Kane-Zibiak model, and I don't have time to show results from that, but even with a simpler model yet, this is a delayed oscillator model for El Nino based on a paper by Stone et al., which is itself a simplified version of Munich Kane-Zibiak. This is a standard integration of this delayed oscillator model for ENSO over multi-decadal timescales. And here we've sort of perturbed the, if you like, atmospheric wind stress forcing with a multiplicative noise. I should explain all the stochastic parameterizations I've showed you so far have been with multiplicative noise. And you get something very similar, a reduction in the variance of the ENSO spectrum and a reddening out from this very periodic multi-year spectrum to something much similar to observations. Just as an aside, well, two asides, you don't get any such effect from additive noise, so this seems to be an intrinsic property of multiplicative noise. And I just want to point out something which people often say to me. They say, oh, all this stochastic noise is just increasing the variability of the model, and we've got enough variability anyway. Well, actually, in this integration, as in the NCAR integration, the variance actually goes down as a result of the stochastic. This is the variance, which is actually halved with this level of noise. And then actually it goes up again as the noise gets even bigger. But for a range of noises, you actually reduce variability. So again, one of the sort of slightly paradoxical, perhaps, nonlinear effects of noise. Okay, now I'm coming to the third point, and really what is perhaps the most important point of this talk. If one buys into this idea that parameterization is inherently stochastic, and think of this as a spectral model with the total wave number and the zonal wave number. So this is the traditional triangular truncation of a spectral model like the ECMWF model. So you've got all this stochastic parameterization here beyond the truncation scale. It's clearly inducing some level of stochasticity into the high wave numbers. So that raises the important question whether we are actually over-engineering our models, not only the parameterizations themselves, but the dynamical core in particular, by using our traditional double precision bit reproducible computations throughout. And in particular then, are we making inefficient use of computing resources that could be otherwise used to increase resolution? Oops. So here's just something, just a tantalizing result. My postdoc, Peter Dubin, has recoded the entire IFS in single precision. This is a highly non-trivial task because it's not just a question of setting all the variables to single precision. You find that there's a lot of very sloppy coding goes on when you just do everything in double precision. You have to actually, so the code will almost certainly fail. And you have to go through, and when you have things like you're subtracting two small numbers, you take out the common factor before you do that, and then it all works fine. So what's shown here are some, CRPS, continuous rank probability scores, for the ECMWF ensemble run at T399 over a number of initial, I can't remember now how many initial dates there are, but anyway, a number of initial dates. And there are actually two curves. You can't see them because they lie exactly on top of each other. One is double precision, and the other is at single precision. This is a T850 and Z500 at CRPS. So there's really no daylight at all between these two. And it turns out, at ECMWF, we run the ensemble out to 15 days, but with a resolution change at 10 days, which is a really awkward thing and induces some shocks particularly in the tropics at day 10. Turns out for the cost of the 10-day run at double precision, we could run to 15 days with the T639 at single precision. And I hope that's something that will be considered seriously at ECMWF. So double precision is 64 bits here, broken up into the mantissa or significant and the exponent. 32 bits of single precision. Now, in principle, why not go to half precision, 16-bit numbers? And it's sort of tantalizing to ask the question whether, in fact, there are many aspects of our models, the parameterizations, perhaps aspects of the Earth system components, which in a way are sort of glorified parameterizations in many respects, and even maybe the high wave numbers of our dynamical cores, which would actually not degrade substantially with 16 bits of representation of information. Unfortunately, at the moment, the computer manufacturers, the chips don't really support this type of half precision or less. And I think an important thing, at least I'm trying to do, is lobby the manufacturers. I'm very much in negotiation, or discussion rather, I should say, with IBM about this issue. And I think they're quite sympathetic to produce chips that really can, or computers which allow really mixed precision arithmetic. Okay, but before that happens, there are actually tools one can use to emulate reduced precision, so-called overloaded operators, and we're actually looking at parts of the IFS with these overloaded operators to see, indeed, can one reduce precision down to 16 bits without significant reduction. I just want to say this is a paper by Peter Dubin and myself in Monthly Weather Review last year, where we took the Reading intermediate spectral model, sort of precursor of ECMWF, and did some idealized NWP studies. We had a T159 version of the model as truth, and then we had forecasts at sort of various reduced resolutions. So here's this, well, you can't see it, solid black line is the RMS error of a T85, set of T85 runs against the T159 truth, and then these dashed lines are with further reductions of resolution. So you see, as you reduce the resolution, you get degradation of forecast skill. That's what we all know. But then what we did was to, let's take this red one, the red dotted line. We did a T85 simulation, but we took all the wave numbers between 31 and 85 and just reduced them down to 6 bits in the significant. So a major reduction in precision. This meant basically that the cost of the T85 model was about the same as the T73 model, and you see that you've hardly changed the skill compared to the full precision T85 model. I should say, incidentally, that this is a relatively straightforward thing to do in a spectral model because the basis functions are scale-aware. We're trying to see whether, using multi-grid methods, this type of approach could be used in the grid point model, and I'm not really sure yet whether that will work or not. But it seems to me this could be a potential, I mean, people are writing off spectral models, but this could actually be a potential advantage for the future for a spectral model because it has this explicit scale dependence. I've talked about software, but there are also issues to do with hardware as well. Actually, Shukla himself introduced me to an article by a chap called Krishna Palem, who now works at Rice University in Texas, who was promoting the idea of stochastic processors, the idea being that for a significant reduction in the voltage across the transistors, and hence the energy demand by the transistors, we can get occasional errors and hence some probabilistic types of processors, but with major reductions in energy costs. And a related idea, which again we're working with Krishna Palem, is that, and again we're using the Reading spectral model to do this, to identify parts of the floating point units where certain types of calculations are hardly ever used and in some sense the electronic circuitry can be pruned accordingly. And finally, there's a whole type of hardware called field programmable gate arrays, where you can actually build in this type of completely variable precision into the hardware design. Okay. So my sort of picture here is that if we recognize the inherent stochasticity in any computational representation of the equations of motion that we're trying to solve, we might be able to take advantage of the fact that decreasing precision and determinism, particularly at high wave numbers, will actually not degrade the forecast skill or the climate simulation accuracy, and maybe we can use that that saved resource to, as it were, extend the dynamic range of our models into the cloud resolve scales. So I just want to finish with just coming back to this climate modeling summit. The kind of aim was to, well, the aim I think has been successful, which was to highlight the fact that compared with the spending on satellites and so on, the spending on computer models was, on computing for models was sort of out of balance. However, a real kind of goal was the development of this cloud-resolved global climate model, and I think it remains an important and urgent grand challenge for our subject. I still feel personally that we should be banging on the doors of our politicians and saying, look, if you're prepared to spend $1 billion a year to find the Higgs boson, surely you can afford to spend $1 billion worldwide a year to determine whether we, humanity, are heading for extinction or not. But for some reason, we don't seem to have that sense of urgency. Exascale plus is needed, and I think the only way to get that is to pool resources internationally, just as the high-energy physicists do. I hope that when the first exascale computers come about, the first dedicated one will be, sorry, dedicated too many times in that sentence, to climate science. But I think we need to communicate to the computer vendors that the probabilistic nature of our problem does not require that all the data has to be moved and stored precisely at this traditional 64-bit precision. And it doesn't require that all the chips be exact and bit reproducible. And in my view, we should be thinking about trying to promote a new class of kind of hybrid computer which can take advantage of variable levels of exactness and precision. For sure, we'll still need the traditional exact chips, but they would be a relatively small part of the overall energy bill. And I think there are many other applications for such a concept. 10 to 6.
Thank you.
And this might be the route not only to 1 kilometer, but to 100 meters. Thank you.
That was a very clear talk. Thank you, Tim. Unfortunately, no time again for questions. Okay, one question.
That'd be good.
Kania has her hand up.
That was quite interesting. You said that this reduction in precision is sort of analogous or has a similar effect as stochastic parameterization, whereas random perturbations would not? Is that?
I think what I'm saying is if you buy into this concept of stochastic parameterization, that it means there's a limit to the amount of information, real information, in a variable, particularly a variable whose scale is close to the truncation scale. And my claim is that 64 bits is actually vastly exceeds that real information content. I mean, what exactly it is, I don't know, and it depends probably on the variable and so on. But all these results show 64 bits is much too much.